Okay, Chemistry 3101, Organic Chemistry 1. I saved this section of Chapter 3 for the very end of the lecture. And the reason why is because Section 3.5 is brand new to the fourth edition of the textbook. It wasn't in the third, second, or first edition, and I taught organic chemistry from those for the past, half a decade or so. And what this section deals with is more of Bronsted-Lowry acidity, but now we're going to talk about assessing the relative acidity of cationic acids. And everybody here knows what a cation is, so we're going to be talking about some kind of acid that's got a positive charge. Now, previously, when we were talking about relative acidities of uncharged acids like HA and HB, and it could be any acid, what we did is we compared the stability of their conjugate bases, and we used the concept of aereo, right? We looked at this conjugate base, and we looked at this conjugate base, and then we compared the stability, starting with A for atom. So we started with A for atom, and then after that, R is resonance. So if the negative charge is on the same atom, then you go to resonance. If there's no resonance in structures, you go to induction. So induction, you look for electron withdrawing groups or atoms. And then finally, you'd go to orbital. If you didn't have any of those other things to differentiate between the two conjugate bases, you would move on to orbitals. Well, if we're talking about acids that have a positive charge, so like HA plus and HB plus, I just have a couple of examples here. Here's an ammonium ion and a hydronium. Well, there's a myriad of factors that can affect the stability of cationic acids, and so the only thing that we're going to focus on is atom. We're not going to focus on resonance, induction, or orbital, so we're actually going to keep it much simpler than we did when we were looking at conjugate bases. And if you look at these two cationic acids here, and if you're wondering, how do I know it's a cationic acid? Well, number one, they're both cations. And number two, they both have protons that can be donated, right? We have the ammonium ion that can donate a proton. So ammonium, and you would have seen ammonium in a buffer, in an ammonium buffer in general chemistry 2. And of course, this is hydronium, which is the conjugate acid of water. Well, if you were comparing these two acids and you didn't know their pKa's, you'd say, okay, well, how do I know which one is stronger and which one is weaker? Well, the difference between the two can be qualified by looking at the atom that bears the positive charge. We know that nitrogen is less electronegative than oxygen, right? If we just think about our electronegativity values, nitrogen has an electronegativity of 3.0 and oxygen has an electronegativity of 3.5. So if nitrogen is less electronegative, then it would be better at stabilizing the positive charge. Put another way, this molecule, or this ion, I should say, this cationic acid is more stable or more content. If it's more stable or more content, that means it doesn't really want to donate a proton, or it wants to donate a proton less than this, because the hydronium ion is less stable. Think about it. Your oxygen is the second most electronegative element in the periodic table. It doesn't want to be positive. It wants to be either neutral or negative. So it's like, get this hydrogen atom off of me. Because if it ends up donating a proton, right, if it loses H plus, then you gain water, and the oxygen atom in water is much more comfortable than it is when it has a positive charge on it. So if we have the more stable acid, that means it's going to be the weaker acid. If we have the less stable acid, that means it's going to be the stronger acid. And so we can ask ourselves, or we can just kind of hypothesize that this should be the stronger acid. Is it? Well, if you compare the pKa's of the ammonium ion and the hydronium ion, you see that hydronium is much stronger. It has a pK of negative 1.7, whereas the ammonium ion has a pK of around 9. And so if we have a weaker acid, it produces a stronger base, a stronger conjugate base, while a stronger acid produces a weaker conjugate base. And that's why amines, like ammonia, are stronger bases than water. We don't think of water as being a strong base, do we? We think of water as having the capability of behaving like an acid or a base, depending on the situation. But ammonia is significantly or a significantly stronger base than water. Now, ammonia isn't a strong base like hydroxide. Okay, it's not that strong, but amines, generally speaking, are stronger bases than water or alcohols. And so that is the rationale. Again, we just looked at the positive charge on a nitrogen versus an oxygen, and we say, well, the positive charge is less comfortable on an oxygen, so that hydronium wants to get rid of a proton, therefore it's going to be a stronger acid. Well, that covers having a positive charge on two atoms that are different, like a nitrogen and an oxygen. But what if you have a positive charge, excuse me, on two atoms that are the same? How would you determine which one of these is more acidic? Is it the alkyl ammonium ion that's most acidic? Or is it this aryl ammonium ion that's more acidic? Well, in order to determine that, what we're going to do in this case is we're going to go back to conjugate bases again, just like we did in section 3.4. So if this loses a proton, we end up with an alkyl amine. And if this loses a proton, we end up with an aryl amine. Now we're going to compare these two conjugate bases. Do you remember that at the end of the lecture yesterday, we talked about Lewis acids and Lewis bases, and we said that a Lewis acid was an electron acceptor, and we said that a Lewis base, was an electron donor. What that means is that the greater ability something has to donate electrons, the stronger base it's going to be. So let's focus on the electrons here on this nitrogen and the electrons here on this nitrogen. I'll highlight them in green. Which pair of those electrons, or which pair of electrons do you think is more available to donate, for donation? Well, the answer would be the pair in yellow. Now, why would that be? It's because the pair that's in yellow is localized. It is stuck there. These are localized. They're not going anywhere. There's no resonance structures that you could draw for that lone pair. However, the lone pair on the aryl amine, they're not localized, are they? They're not nearly as available because they're delocalized, and we could draw a whole collection of resonance structures for this aryl amine. And so if we I guess I repeated the same slide here. Anyhow, so we see that since the lone pair on the aryl amine is delocalized, that it's going to be a weaker base because, again, a base is an electron donor. So if we have a weaker base, what does that mean? It means that its conjugate acid is going to be stronger. It's going to want to lose a proton more than the conjugate acid of the alkyl amine. And that's the rationale, nothing more than that. So we've looked at two types of comparisons for cationic acids. One's where you have a positive charge on atoms of differing electronegativity. So we used electronegativity to solve the problem. And now we're looking at positive charges on two atoms that are the same. But what do we do now is we look at the conjugate bases. And we compare the lone pairs on the nitrogen and say, well, which pair is less available? The pair that's less available is going to produce, or is going to result in, a weaker base, and therefore it's going to result in a stronger conjugate acid, and that's exactly what we see here. Now, I don't expect you to memorize the pKa's of every single alkyl cationic or alkyl amino cationic acid, or every aryl ammonium cationic acid. However, I would think that it's a good idea to have a rough idea of ammonium ions and their pKa values. And I can summarize this for you very quickly. You should know that ammonium, which is a very common ion, so ammonium has a pKa of around 9. So we'll just choose 9 for that. If you have an alkyl ammonium, it affects the pKa slightly. So any kind of alkyl ammonium, meaning that the R groups are just alkyls, that will have a pKa of somewhere between 10 and 11. And if you have an aryl ammonium, again, since an aryl amine is a weaker base, it produces a stronger conjugate acid. So as long as you know that it's around 5. Okay, so 5-ish is close enough for me. That's good enough. So these are some more pKa values that you would want to add to table 3.1. So Memorize, we'll put memorize plus table 3.1, which is extremely, extremely important. Just one last thing I'll say about a lone pair on a nitrogen. You might think, okay, well, I just saw the lone pair on the aryl ammonium, or sorry, the arylamine and the alkylamine. You know, I have a lone pair, it's basic. Every time I see a lone pair on a nitrogen, it must be basic. That is not true. If you take a look at an amide, okay, if we take a look at an amide, we drew the resonance structure for an amide in chapter 2, and we see that the lone pair on the nitrogen is delocalized. Since that lone pair is delocalized, amides are extremely poor bases because that lone pair is not available to be protonated. It is delocalized. It is not just sitting on that nitrogen waiting to be protonated. And so the resonance effect is so, if you have your mic on, could you turn it off? Somebody has their microphone on. Anyhow, the resonance effect is so strong that amides, generally speaking, will not function as bases. Kind of interesting, huh? Anyhow, and that covers all of section 3.5, and that is everything I expect you to know from that section. Not much more than that. So I'd say the take-home message was the whole atom thing, and then the localized versus delocalized electrons, and then knowing these three pKa values. So an ammonium is 9, an alkyl ammonium is around 10 or 11, and an aryl ammonium is a stronger acid. It's around 5-ish, and that's good enough for me. All right, well, that's enough of section 3.5. We covered everything in this chapter, including Lewis acids and bases, the very last section. So I want to switch gears and try some practice problems. So let's take a look here. So grab yourself a pencil and a piece of paper, and let's work on some practice problems. So chapter 3, practice. And I'm going to ask you some questions here. So I have the chat open. And if you want to unmute your mic to answer a question, feel free to do that. So first thing we're going to try doing is we're going to try draw the conjugate base. So draw the conjugate base. All right, and we're going to start with a couple of molecules here. So we'll start with this. So that's just plain old ethanol. We'll start with this ketone. Put it on my lone pairs here, and let's do ammonia. Okay, so I want you to try to draw the conjugate base of all three of these. Why don't we add another one in here? Let's put hydronium in here too, just to make things interesting. So we've got 4 questions here. Question 1, 2, 3, and 4. And we're just trying to draw a conjugate base. Could anybody either type in the chat or unmute their mic and describe to me what the procedure would be to go about drawing a conjugate base? Well, how will the structure be modified when we're drawing a conjugate base? So that would mean we're treating everything here as an acid. Tracy says you're going to lose a proton. That's absolutely correct. Yes, right? So we'll put here conjugate base, put here results from loss of H+, right? Because you have an acid, for example, let's say you have HA. When it donates a proton, you end up with the conjugate base. Okay. So could anybody describe to me in question 1 which would be the most acidic proton, where I would locate that most acidic proton in the first one? Yeah, it's going to be the hydrogen that's on the oxygen. Absolutely. Right, we know that this is an alcohol. Okay, so we'll write that in here. This is an alcohol. And we know that the pKa of an alcohol hydrogen, pKa is around 16 to 18. Every other hydrogen in here, these 2, these 3, these are all just plain old sp3 carbon hydrogen bonds. So all the pKa's here are around 50. So pKa is going to be about 50. You could solve it using pKa values that you have to memorize, or you could have solved it using area. The hydrogen on the oxygen, well, oxygen is more electronegative than carbon. They're in the same period, and therefore it would be this hydrogen. So if we lose that hydrogen as H+, what are we going to be left over with? We're going to be left over with this, where we have 3 lone pairs on the oxygen, and now we have a negative charge. That would be our conjugate base. In question 2, I'm going to label some protons. What if I put these protons, put this proton in red, and what if we put these protons in green? We'll just start with those ones, okay? Could anybody tell me which would be the more acidic protons, the ones in red or the ones in green? Which would be more acidic? Yeah, the ones in red are going to be the most acidic. Absolutely. How do I know that? Right, how do I know that? Well, both of the sets of protons are on carbons, so we can't use atom if we're thinking about aereo. We can't use atom because they're both on the same atom, but we can use resonance, can't we? Because if you remove one of the protons in red, you end up with this conjugate base. So we end up with a negative charge here because we've lost the hydrogen. And we know that we can draw a resonance structure for this carbanion, can't we? Where we show the delocalization of the lone pair. And so that is going to be the most acidic, or those would be the most acidic hydrogens. So we have the resonance structure that we could draw here. If you were to remove one of those green hydrogens, which would not produce the conjugate base, but you'd end up with this, okay? And the problem with this is that there's no resonance structures that can be drawn, and therefore the answer is to remove one of those protons in red, and this would be your conjugate base. And if you're wondering, well, could I have drawn it like this? Sure, either one is perfectly reasonable. Now, if you're wondering, could I solve this using pKa's? The answer is yes. I'm not going to go back to table 3.1. However, if you go to table 3.1, in table 3.1, they have this molecule, which is acetone, and the protons in here have a pKa of around 19, right? These protons here, I'll just draw 1 in here, and you can see that this is a ketone, like acetone in here. And so those are going to be, again, the most acidic protons, and that is how you would use table 3.1. The protons in green, again, are just sp3 carbon hydrogen bonds that are not part of the ketone functional group, and therefore they would have a pKa of around 50. There we go. Go ahead.
So why wouldn't I be able to take a resonance structure from the green?
Because there's no sp2 hybridized carbon adjacent to the negative charge, right?
Okay.
In order to draw a resonance structure, you'd have to have an sp2 hybridized carbon. Just let me try to delete this thing here. Delete. There's no sp2 hybridized carbon here or here, right? You go back to the patterns that we looked at. So we looked for allylic lone pairs. This lone pair is not allylic to anything, so there's no way that we could draw any resonance structure for that, right? But if you go back to this resonance structure here, okay, we see that this is an allylic lone pair, right? You have the lone pair, you have an sp2 hybridized carbon on a double bond, and so we can draw a resonance structure here. So what you want to do is go back to chapter 2 and review all the different rules and patterns that we looked for when we're drawing resonance structures. Does that make some sense?
Yes, thank you.
Yeah, no problem. Okay, what about ammonia, NH3? What would be the conjugate base of NH3? Could anybody type it in the chat or unmute their mic and just holler it, just yell at me? This is the conjugate base. Don't worry, I won't be offended. I'd be happy. Could anybody tell me what the conjugate base of ammonia would be? NH3, it loses. Yeah, absolutely. Kiana, put it in the chat. Right. So remember, if we're losing H plus, what we're left over with has to be negative, right? If you have, if you have something that's neutral, a molecule that's neutral, this is neutral, it has no charge. If it's losing H plus, right, what's the other thing has to be negative, because -1 and +1 gives you 0. So that means the conjugate base of something that's neutral is always going to be negatively charged. So we end up losing a proton from the NH3 and we get NH2, but it's negative. Now, if you want to draw the Lewis structures, right, if we draw the Lewis structure of ammonia, it's NH3 like this, but when it loses minus H plus, you end up with NH2, and now you've got 2 lone pairs, and that's why it has a negative charge, right? Go back to your formal charge. Nitrogen has 5 valence electrons, subtract 2 sticks and 4 dots gives you -1. All right, so there's our conjugate base for ammonia. And the last one, what would be the conjugate base for hydronium? Anybody? Loses H plus, what do you end up with? You just end up with water. Exactly. You just end up with H2O after it loses a proton. Great. Okay, let's try something a little bit different. Let's try drawing some conjugate acids. So we'll put in here, draw the conjugate acid. All right, let's try some problems here. So we'll start with this one. We have this carbanion, and we'll try this one. We could try, what else? We could try this alcohol, and we could try this ketone, and then we could try this amine. So we've got 5 different problems here. 1, 2, 3, 4, 5. Draw the conjugate acid. So how do we draw a conjugate acid? Can anybody tell me the quick answer for what do you do when you want to draw a conjugate acid? How do I draw a conjugate acid? I add a proton. Absolutely, Alexandria. So we'll put here, add a proton, or H plus. All right, so I'm going to do this one a little bit faster. We have the negative charge here. We're adding H plus to it. Keep in mind that there are already 2 hydrogens bound here, right? This carbon has a negative charge, so it's got 3 bonds and 1 lone pair. We're going to add a hydrogen to that. We would just end up with this molecule, which is butane. The next one, we're going to add H plus to this carbanion right here, and we're going to end up with this ketone. So when we add H plus to that, could anybody tell me where I would add the hydrogen in 3? which atom would I add the hydrogen to? I can't add it to a carbon. Right, thanks, Luke. I can't add it to a carbon because if I did that, then the carbons would have 5 bonds. I can't add it to a hydrogen because a hydrogen can't have 2 bonds, but I do have an oxygen, and an oxygen has a lone pair to donate. So if we just had H plus, then we end up with the conjugate acid being OH2, like this, which has a positive charge. Sometimes you'll see me write a partially condensed structure like this, where I'll just write OH2 and then put the lone pair in the positive charge. Instead of drawing all the bonds explicitly, I'll just condense it a little bit like that. So if we follow the same rationale for the ketone that I have in number 4, the only place that I could add a proton is to the oxygen, because none of the carbons can take on an extra bond. And so we add the hydrogen atom to the oxygen, and I end up with an oxonium ion, like this. Could anybody tell me, I know that you spent last night practicing table 3.1, could anybody tell me the pKa for this ion that I have in the black box? Even just approximately? That was one of the first pKa's covered in table 3.1. Exactly. The pK is negative 7.3. If you just know that it's negative 7, that would be good enough for me. All right. And the last one is an amine. We have a lone pair on the nitrogen. It's the only thing that can take on a proton. So when we draw the conjugate acid, it's going to look like this, NH3 plus, just like that. And we just studied these a few minutes ago, and we said that the pKa of an alkyl ammonium ion, the pK is around 10 to 11, something like that. All right, good practice. Let's try some more. Let's take a look at, let's try this question. So if I had a compound that has a pKa equal to 10, and I compare that to something that has a pKa of 7, what I want you to tell me is that if something has a pK of 7, it's obviously more acidic than something that has a pK of 10. How many more times acidic is something that has a pKa of 7 than something that has a pK of 10? Could anybody tell me? It's 1,000 times, exactly. Right? Because if you take 10 and you subtract 7, that gives you 3. So then you say, well, each one of these log units represents a magnitude of 10-fold. And so we have 10 to the power of 3, which is equal to 1,000 times more acidic. All right, good. Okay, so we've covered that. Let's try a question. And this is one from our textbook. I don't know exactly which number it is, but I thought it was a fun question. It says, if you try to do this reaction, so if you take this terminal alkyne and you react it with NH2 minus, and you want to make this compound, so this terminal alkynide plus NH3. The question asks you, would this reaction work in ethanol, which is CH3CH2OH? So it's an alcohol. The first thing I want to just cover with you quickly are the pKa's of the, so this is our acid, this is our base, this is our conjugate acid, and this is our conjugate base. And make sure that the reaction's written out correctly. Our acid, which is the terminal alkyne, this proton has a pKa of 25, whereas the conjugate acid, ammonia, has a pKa that's 38. Equilibrium will lie to side of weaker acid. And so this is perfectly reasonable. So we give that the old checkaroo. There's nothing wrong with that. But the question is, would this reaction work in ethanol? Could anybody tell me what the pKa of an alcohol is, roughly? I know that we covered ethanol in yesterday's lecture, but could anybody tell me what the pK of ethanol is? I'll just scribble it down here. pKa is equal to, anybody? You have to go back to table 3.1. There's no problem with that. Yeah, thanks, Kiana. Exactly. The pK is 16. Okay, so let's imagine you had ethanol. I'm going to write it in green. My students usually don't like the green pen. It's hard to see. At least on the PowerPoint it is. Anyhow, would ethanol work? Would it work? Well, you've got to ask yourself, would the ethanol react with the base? Because an ethanol is an acid. So let's see here. If the base remains intact, then we're good. But if the base would rip a proton off of ethanol, then we're in trouble. So let's write this down. If you had ethanol in your reaction mixture, and then it sees some NH2 minus in the reaction flask, what could happen? The amide, NH2 minus, could pull the proton off of ethanol to make ammonia, and then we're left over with, this is called ethoxide. So if we compare the pKa's of ethanol, the pKa is equal to 16, and the pK of ammonia is equal to 38. Let me ask you, would ethanol work as a solvent for this reaction? Yes or no? Did anybody answer it? The answer is on here. Would this be a yes or a no? Exactly, exactly. Thanks, Luke. The answer is a big no. You would destroy your base, because when the base sees ethanol, which this is supposed to be your solvent, question mark, well, it's not going to work because it's going to rip the proton off the solvent, and then this would be your base is destroyed. It's converted into ammonia now, and your solvent is destroyed. It's not ethanol anymore. Solvent is, and I don't mean it's destroyed like it was burned up, but it's not intact. I mean, maybe it's just destroyed as a harsh way of phrasing it, but it's not intact anymore. All right. Let's try another one here. Let's try drawing some curved arrows. Let's try drawing some curved arrows. So let's see here. So if I gave you an acid and a base, so let's try writing out sulfuric acid. Son of a gun, did I just lose everything that I drew? Yep, it's all gone. Okay, so let's draw some sulfuric acid, H2SO4. There we go. So everybody should know how to draw the Lewis structure of a strong acid like sulfuric acid. And if I put that in water, H2O, it's going to end up protonating the water to produce hydronium, which is my conjugate acid. And I'm going to be left over with the hydrogen sulfate ion. I'll draw out the entire Lewis structure of that. So what we want to do is draw the curved arrows. So we'll put here draw mechanism. Draw mechanism. Okay, so what's my mechanism going to look like here? Could anybody tell me where I would start the tail of my first curved arrow to show the transfer of the proton from the sulfuric acid to the water, right? This is the proton that's being transferred over to the water molecule. Could anybody describe to me, maybe unmute their mic and tell me, or type in the chat the best they can, where would my tail of my arrow start? On which atom and which molecule?
I believe the tail of your arrow is actually going to start on the lone pair in the water and go to the H.
Exactly. Perfect. Who said that?
That was Luke.
Hey, Luke, how's it going? That is perfect. Exactly. I couldn't have described it any better myself. So Luke says the tail of the arrow is going to start on the lone pair of the water. It's going to attack the sulfuric acid. It's going to grab that hydrogen. But we know that this lone pair, in the bond isn't just going to float there in outer space, once you remove that hydrogen. So now you're going to break this bond and you're going to put the lone pair on the oxygen. So that's where that lone pair ends up, this lone pair from this bond. There we go. Let's try another one. I thought this was an interesting one. Again, this comes from the textbook. In fact, most of these problems come from the textbook. I just think I picked the ones that I think are really good. So this one, they put everything in the same molecule. So you have a molecule that has the conjugate base and the acid, or the base and the acid in it. And it says, draw a mechanism going from here to here, where we have a negative charge on the oxygen. We still have this. And now we have a nitrogen with a hydrogen attached to it. Excuse me. Like that. So in this reaction, this portion of the molecule is behaving as the acid, and this portion of the molecule is behaving as a base. And we're transferring, excuse me, this proton over to the nitrogen. Could anybody tell me where the tail of my arrow would start for my first curved arrow? Again, not a trick question. Mr. Dion does not like trick questions. Yes, absolutely, Andrew, 100% correct. Yes, it's going to start on the lone pair on the nitrogen. You could start it here, you could start it here, doesn't matter. Sometimes you'll even see people just start it on the negative charge. I don't really like that a whole lot. So we'll start on a lone pair. We're going to attack that hydrogen, but now we got to do something with this bond because we need another lone pair over here. So we're going to draw the pair of electrons going onto the nitrogen. And there we go. Hot dog, we have a wiener. Perfect. Let's try one more, and then maybe we'll move on to chapter 4. Let's try a couple more here. Let's see. I think this is a good question. So it says rank the question is rank in terms of increasing basicity. So if you have hydroxide, and then you have, this is called acetate. I showed you this the other day. So acetate, then you have tert-butoxide, which is this guy here. And then you have and now this ethoxide. Okay, so we want to rank them from least basic, so least basic down here, and then we're going to go all the way up to most basic. So we have a bunch of conjugate bases here. The negative charge is on an oxygen for each one of them. So if we're using area as our strategy, excuse me, we can't use atom, but can we use resonance? Well, there's only one of these that has a resonance structure, right? If I call these, A, B, C, and D, could anybody tell me which one of these has a resonance structure? The only one with a resonance structure? Yes, absolutely. It's B. B is the only one with resonance, and therefore its lone pair is going to be the most stabilized because it's got the resonance structure. And so since it has a resonance structure, that means that the lone pair is less available. So therefore that would be the least basic of all 4 of these. So we could put the acetate down here to start with. We could just write acetate ion down here. But there's another way to solve this problem and a better way to solve this, and that is using pKa values. So what we're going to do is we're going to draw the conjugate acid of each one of these, and I'm going to draw a little bit faster. The conjugate acid of hydroxide is water. The conjugate acid here is a carboxylic acid. The conjugate acid here is tert-butanol or tert-butyl alcohol. And the conjugate acid of this is ethanol. Now I'm going to write in the pKa's. I memorized that the pK of water was 15.7. For a carboxylic acid, it was around 5. For tert-butanol, it was 18. And for ethanol, it was 16. Now remember that the least basic of those anions is going to have the strongest conjugate acid. And the most basic is going to have the weakest conjugate acid. So now we can just look at the pKa's of the conjugate acids. Which one is the strongest of all? The strongest conjugate acid is the acetate ion. So we'll put that down here. This is the least basic of all of them. Which one is the weakest acid? The weakest acid is the tert-butanol. It has the highest pKa, therefore it would produce the strongest base. So this is going to be the strongest of all the bases. Now I just have to look at the ethoxide and the hydroxide, and you can see that water is slightly more acidic than ethoxide, and therefore that means the hydroxide is going to be a weaker base. So we'll scribble hydroxide down here, and then we'll put ethoxide like that. So we start with the acetate, which is the weakest. Then we go to hydroxide, ethoxide, and the tert butoxide is the king of the castle, the strongest of all of them. And this is why you must memorize table 3.1. There would be no way for you to solve this using area. Could not do it. You have to have those values in your noggin in order to solve this problem. Any questions about that one? And don't hesitate at any time to stop me and ask me a question. Excuse me. Okay. So table 3.1. Does anybody think they have the whole thing memorized? All of table 3.1? Or even 80% of it maybe? All right. All right. Well, you gotta, good. I'm glad you like going over practice problems. You gotta go over practice problems. It is the only way to master organic chemistry. You can see how doing practice is very useful for students and instructors alike. Let's try one more problem and then we'll move on to chapter 4. So one more problem. We're gonna get some aereo practice. So let's practice aereo, okay? And what I'm gonna do is I'm gonna draw a compound for you here. And I want you to tell me what's the most acidic proton. So most acidic proton. We'll put that question mark. Okay. So let's see here. Let's try this molecule. And again, I took this question from the textbook. There we go. If we have this molecule, and then we'll try it. I'll draw another one down here. So where I have this, then I'll put it on here, and here, and here. Okay, let's start with the first one. So that's this guy right here. Could anybody tell me which is the most acidic proton in this molecule? Just describe it to me. What would be the most acidic proton? Yes, Kiana, absolutely. It's the one on the sulfur. Now, Kiana, I'm not sure how you solved that problem, but I know that you used one of two ways, and maybe you used both ways, if you wanted to double check. Kiana could have said, okay, well, I've got a hydrogen on a nitrogen, and then I've got one on an oxygen. And I know that oxygen is more electronegative than nitrogen. And so that's going to better stabilize a negative charge. So this would be more acidic than the proton that I have highlighted in green. Then if I compare the hydrogen on the oxygen versus the hydrogen on the sulfur, well, those two atoms are in the same group or family, and sulfur is larger than oxygen, so it is going to more effectively stabilize a negative charge than oxygen. And therefore, she used, if maybe she used atom to solve this. Said, okay, well, sulfur is going to best stabilize the negative charge of the conjugate base, so most acidic. Okay, and that's one way of solving it, and there's nothing wrong with that. However, there is another way to solve this. If you remember the pKa values, the pKa value for an alcohol, pKa is around 16 to 18. The pKa for an alkyl amine, is somewhere around that of ammonia, so we'll put pKa is around 38-ish. Okay, whereas yesterday I showed you that when we talked to H2S, they had a pK of around 7. It was around 7. So that means that the pK of this would also be around 7, because if you have H2S, it's this, and all you're doing is replacing one of the hydrogens with an R group. It's not going to affect the pK all that much. And again, you see that this is going to be the most acidic because it has the lowest pKa. So you could have used A from aereo, or you could have used pKa values. Either one would work. Okay, the next one, there's a lot of protons in the next molecule. And so I highlighted just 3 of them to make it a little bit simpler. Could anybody tell me which one of these would be the most acidic proton? Would it be the green, the red, or the blue one? Heck yeah, it's the red one, isn't it, Andrew? Andrew, could you tell me what your strategy was to solve that? Or anybody? Could anybody tell me what their strategy was? Yes, absolutely. Absolutely. So Andrew said, well, I can't use atom to solve this problem because those protons are all on carbons. We have a carbon here, we have a carbon here, and we have a carbon here. So if we have aereo, we can't use atom. But he said, well, if you remove the proton in red, it would produce a resonance structure because if you had a lone pair here, it would be allylic. If you have a lone pair here, it would not be allylic. And we know that when you have a carbon-hydrogen bond that's sp2 hybridized, it has a pK of around 44. So the pK of this is around 44. Okay, so that's pretty high, and we generally don't make vinylic carbanions. So I'm just going to erase this right now. But he said, I'll use resonance, and he'd be 100% correct. So if you lose H plus, the H plus in red, maybe I should color code my work. So we'll lose H plus, and then you end up with this carbanion. This, okay. Now, can you draw a resonance structure for that? I hope so. This is something that you need to do or need to be able to do. So you have to delocalize this lone pair, and then we're going to put this pair of electrons up here. We're going to draw the resonance structure like this. So now we've got a double, oops, that's not very pretty. We've got a double bond here, got a lone pair here, and our gem dimethyl. So resonance was the tool that he could have, or that he used to solve this problem. I don't know. Let's try one more, and then I guess we'll move on to chapter 4. As you can see, Mr. Dion enjoys doing practice problems too. All right, let's try this one. A neat molecule. Again, I took this from the textbook. It's where I get all my best ideas. So if we use this, and then over here, we have this one. All right, so we've got an alcohol, we've got an amine, and we've got a carboxylic acid. And I want to know which proton is the most acidic. I'll make it a little simpler. We'll highlight this one in yellow, this one in red, maybe this one in green, something like that. Could anybody tell me which one would be the most acidic here? Okay, so if we look at these three protons and we think of aereo, okay, we have protons that are on oxygens, and then we have two protons on a nitrogen. Oxygen has an electronegativity of 3.5, whereas nitrogen has an electronegativity of 3.0. Therefore, since oxygen is more electronegative, the oxygens would be more comfortable with a negative charge than a nitrogen would. So that takes the nitrogen out of the running. It is not going to have the most acidic proton. So now you have the oxygen, the green oxygen atom, and you also have the red oxygen, or sorry, yeah, the green proton and the red proton. Sorry, I'm thinking of too many things at once here. Anyhow, and what's interesting is that you could draw resonance structures for both of these. Okay, if you were to draw the conjugate base here, and I'll just kind of adulter the structure. Okay, if you were to draw the conjugate base here, you could draw a resonance structure like this. There's nothing wrong with that, so erase that. And if you were to, deprotonate here, then the same thing would apply. You could also draw a resonance structure here where you would put, no, sorry, you cannot draw a resonance structure. Mr. Dion is losing his marbles. So that is why it's a good idea to do practice. There we go. So the only one that you can draw a resonance structure for is this one. So you don't use atom, you would use resonance. And so the proton highlighted in red would be the more acidic proton. So we end up drawing this compound. There we go. And we can draw the resonance structure after you've lost H plus, where you end up with the resonance structure that looks like this. So we have our hydroxyl here, and have something that looks like that. There you go. So those are the two resonance structures. And so we would use R or resonance to solve this.